So um, there was some discussion about like Clang versus GCC compile times, and in an effort to determine why Clang is slower, I've instrumented Clang with Perfetto, which is Google's replacement for Chrome tracing. Um, so when you run Clang with this Perfetto flag, it produces a trace file um, that has like custom trace events that will come up in the Perfetto viewer, and you can go through and look at where we are spending time compiling stuff. So um, this is a compilation of just an arbitrary kernel source file. I just picked one at random. Like you can click on the source on these slices and you can see like down here, this is including this header file. And you can like click on these optimization passes and see what function is being optimized here. And you can click on like the actual pass and you can see the name of the pass itself. So these trace files, you can make shareable links for them. And when you send somebody one of these links, they just open it and they get the exact same view that you have. There's a query engine that you can use to basically do analysis on your trace. So here we see we're spending 2,400 milliseconds in the front end, 3,700 in the back end. And what's really nice about this is you can concatenate these traces together with just Linux cat. So if you do a build of the kernel and you take all these trace files and you just cat them all together, you can get something that looks like this. And you can see all of the translation units together, and you can do queries on these as well. So these are in seconds now because they got really big, but we spend 2,500 CPU seconds in the front end and 600 in the back end. And same thing with these shareable links. Pretty useful. I haven't really done too much analysis on the actual traces themselves. I've mostly spent the last 2 weeks and up to like 30 minutes before this meeting getting the tracer to work. So yeah.
So is this a live demo or is this
This is with the most recent changes that I've made. This is essentially what I'm planning on posting to Fabricator.
Great. So it sounds like
what kind of changes do you mean? Did you make changes to the kernel or to the compiler or both?
To the compiler. Okay. So I've had some amount of issues with getting Perfetto to work, just in general. Like these slices are actually like limited based on slice size. So if the slice is not larger than 2 milliseconds, it doesn't get recorded. And I've had quite a few issues fixing that. So now everything seems to work. But yeah, it's just changes in the compiler with the actual tracing.
Nathan, can you give a little bit more details on how did you instrument the compiler for this Perfetto?
Yeah. Here, I can actually pull up. So so Perfetto itself exposes like the C++ API. So you link it with, you link the Perfetto library with CMake. So here's the CMake commands that I've added. So it pulls the Perfetto GitHub when you build, and then it automatically links it everywhere that it needs to be linked. And then there's some macros that were defined in in the compiler, and whenever you want to record a trace event, you just do like LLVM trace, and yeah, you just call this LLVM trace macro, and it will record your trace through Perfetto if you have Perfetto enabled. And then to build with Perfetto, you have to pass a CMake configuration flag to your CMake command. So you'd have to do like -d Perfetto when you're building Clang.
And what is it that you are tracing, the different starts and end of phases, or what? Or
yeah, so there's 3 different macros that I've added. One is here. Let's see if I can find it. I don't know exactly where they are here, but you can do like LLVM trace scope, which creates like an anonymous struct, and then when the struct goes out of scope, it ends the. So it creates an anonymous struct, begins a trace event, and when the struct goes out of scope, it ends the trace event. And then there's also LLVM trace begin and LLVM trace end, which are just explicitly beginning and ending trace events. So most places just use this LLVM trace scope because it's more reliable than the LLVM trace begin and LLVM trace end. But yeah, you would just add like an LLVM trace scope macro anywhere that you wanted to have a trace in the anywhere you'd want to have a slice in the trace.
So Huck, I'll add some rhetorical questions for purposes of the reporting, but how does this differ from LLVM's -f time trace or -f trace report?
Yeah, so LLVM-f time trace does essentially the same thing, but for Chrome tracing. So first of all, the traces are smaller. In my limited testing, they're about 3 times smaller. As well as you can concatenate these traces easily. With the f-time trace, you have to do some magic and like actually parse through the file to concatenate them. With this, you just run cat. There's also the query engine that the LLVM f-time trace does not have, and then shareable links as well.
Cool. And with this instrumentation infrastructure in place, what do you think are the next steps for us to start investigating improving compile times with Clang for our Linux kernels?
Yeah, I think some time needs to be spent going through and actually doing analysis on these traces. I haven't really looked into what's going on at all, but currently it seems a bit suspicious that we spend like 5 times more time in the front end than we do in the back end.
Does anyone have any guesses why that might be the case?
Yes.
Okay.
So I just spent the last month on and off looking at improving compile speed of the kernel by reducing the header files, and I'm now at like over 30% improvement with Clang 10 just by reducing the number of header files that get pulled in. And we found earlier, like many times before, that there's one significant difference between the way that GCC and Clang look at files. So GCC, one of the early things it does is that it identifies dead code and completely throws it away, and then it doesn't report any bugs in that code that it would otherwise find, whereas Clang does a lot more processing on all the functions that are visible and then does dead code elimination much, much later. And there's the syntactical analysis and all that, and like tracking uninitialized variables, whatever that does just for reporting errors, that is certainly useful. But I suspect there's also a certain number of optimization passes that happen on unused functions that are then thrown away.
I would also guess GNU-C statements probably cause a lot of that as well, because I know that just came up recently with like the KC sand macros and stuff of that nature.
Now, I think what happened there is that we pass a statement into a macro, and that statement contains another statement that is expanded like a few times, and then the second macro expands it another 8 times. It just explodes. So a single line of code can turn into thousands of tokens.
Yep.
Right. In the case that Nathan's referring to, Clang basically spends a lot of time trying to accurately track what the source location of a given token is when it comes to macro argument expansion for the purposes of reporting diagnostics if there's a warning or error to be emitted. And in that case, there were some kind of pathological cases, where maybe traditionally macro argument parameters are only a few tokens, but in the case of GNU-C statement expressions can be, almost entire function-like kind of macros, which have many, many tokens to be expanded, kind of thing.
So one,
for the particular case, I noticed that like the average preprocessed file size grew from like 4 to 6 megabytes to 30 to 40 megabytes. And I've got it down to like 1 megabyte now with my changes on the kernel.
It's hard to imagine 30 megabytes of input source, but that's only C code. I can't.
That's just header files with inline functions that are never called.
I've actually seen similar cases before. Like, I've run into cases where just changing the order of passes actually, affect the build time a lot. It's similar to that code elimination. So I ran this man to reg pass on LLVM to remove some like useless stack variables, and then run some optimization. It actually, improved the build time a lot. So I wonder if that's the case like here. But like if you want to look into improving build time, that might be one thing you can look at, is to change like the order of optimization passes.
That's a great idea. We always had these discussions of, optimally you would run dead code elimination after every pass, right? A lot of passes can kind of leave behind garbage, and they kind of rely on DCE to clean up after them, which kind of results in like garbage being re-optimized again and again and again, which is tricky. So I think, having these links, like to me, it's like Godbolt, right? Where you can just share the link is incredibly powerful, because suddenly now we can make changes to LLVM where we either reorder passes or maybe we remove passes from the O2 pipeline and say this is only run at O3, and actually quantify and show like, here's an entire build of the Linux kernel. Here's how much faster it is, with or without this change, kind of thing. Being able to quantify things is a very strong argument.
So what I'd like to see is an optimization pass, and that basically just looks at static functions and sees if they are called at all, and then throws away the entire function before we do any other optimization passes. But after, of course, checking that there are no syntactical errors in that function. And that would get rid of most of the contents of those header files. So if we can just free up all that internal state and then start the actual optimization, that might make a huge difference.
So we'd want something like that to run before semantic analysis if we're spending a lot of time in semantic analysis on dead code kind of thing. And there's kind of whisperings, actually. I feel like so like Chris Ladner created LLVM, and at least 2 cases I can think of where he has these kind of shallow digs at Clang itself are his 2015 presentation on Swift and kind of the design of Swift's IR, but also some of his MLIR talks. They actually talk about, how could Clang, move to using MLIR instead of LLVM. And he actually has concrete suggestions where he talks about with Clang, like he kind of points to this asymmetry between Rust and I think maybe Julia and Swift all having IRs kind of before LLVM IR that are more specific to the front end language. And he kind of points to this asymmetry where he says Clang does not. And he says if Clang did, then we could base code gen on control flow analysis instead of doing an abstract syntax tree walk. And at that point, the control flow analysis kind of gives us that information that like this function is entirely unreachable, right, in the front end. And so I think things like that are like wildly different architectural changes that will take years to do in Clang. But I think it seems like we understand pretty well now. A major pain point is the semantic analysis of dead code. And in particular, that's one of the reasons why we still can't build a 32-bit x86 kernel quite yet. Is there's very interesting kind of metaprogramming going on, with some macros that make use of GNU-C statement expressions and use type of quite extensively for kind of it's an interesting form of polymorphism kind of thing, but the hard part is it's really kind of tightly coupled to GCC's ability to throw away kind of dead code before semantically analyzing it. So we have some cleanups there, but there's more work to be done, kind of thing. It certainly is a little tricky, and thankfully we don't have that issue today with other architectures, I think. But I always worry that those could creep back in. So. Awesome. Thanks so much for all this work, Nathan. And we look forward to your RFC this afternoon. And I guess I'll send the meeting notes maybe after that RFC goes out. That way I can send everyone a link that as well. And I look forward to playing with this, and hopefully we can find some interesting and fun, curious bugs. So thank you.
So I do have a quick question. Like, does GCC have similar tool? So like, if you can find a similar tool for GCC, then it's probably easier for you to look at the differences and figure out where we can improve the most on Clang.
I don't think that they do. So on the original ftime trace commit, I remember seeing like some GCC maintainers saying, "I wish I had this for GCC." I don't know if they've implemented that, but that seems to indicate to me that no, they do not.
Okay, right.
I mean, it's always hard to build a tool that will be generally useful to people. I think if we can show that this is an actual useful tool that people can then go and make important optimizations from, this is something that we absolutely should share with GCC developers and show like kind of what's our workflow for addressing these problems, kind of thing. Because I'm sure they have very similar issues that Clang does, right? And performance cliffs that people, it's very hard to understand. This looks like such an innocuous change. Why am I getting such drastic change of behavior?
Agree.
Cool.
I have a question. Is it possible? Yeah, I was wondering which configuration do you use for running your experiments?
This is just with x86 64 def config.
Okay. And do you think it would make sense to change the configuration to see if there is other insights we can extract?
Yeah, probably. I haven't really done any actual analysis with it yet, though. I've literally just been trying to get the tracer to work up until today. So now that the tracer works, actual analysis can start.
Yeah.
I would guess that if you can get some results for def config, the next step would be to try it again for x86 all mod config, which has a number of options enabled that can make a huge difference.
Yeah.
Rand configs probably don't make sense for a while until you have like actual until you have changed a lot of things based on the first findings, and then you can start looking into others. Doing it on other architectures, of course, like building a ARM kernel instead of x86 also makes a huge difference. So especially ARM32 seems to be much slower than ARM64 and x86. So there might be something specific to ARM32 that makes that particularly slow, whatever that is.
Yes,
Could just be that the headers are bigger.
in particular, one thing that's a little tricky to tease out is not only do different target architectures have different kind of source files, different def configs, different sheer amount of lines of code we're throwing at the toolchain. But then what further complicates this is the toolchain itself will have different pipelines based on the target architecture and the optimization level. And so it's absolutely possible that, like LLVM, for example, has 3 different register allocators and 4 different register allocators and 3 different instruction selectors. And which one is used, like they're radically different architectures with wildly different performance characteristics and generated code performance. And they're kind of mutually exclusive. And it could be that different architectures are using wildly different combinations of these kind of thing, which can kind of conflate that further. But having the analysis, absolutely is kind of the starting point. I think before having any like hypothetical discussions, being able to measure is kind of the most helpful kind of thing.